Welcome back to Newton's Laws problem solving. We're going to revisit a problem today that you've seen previously, but we're going to apply our calculus tools to this problem to see if we can't get more insight into the dynamics of what's going on. So on the screen you see this kid that's pushing a sled or pulling a sled. Previously we talked about how pushing versus pulling can increase or decrease the friction force that's involved, right? Because friction is dependent on the normal force, and the way that the kid pushes is going to affect how much normal force there is. So the question we want to tackle is, what's the ideal angle for the kid to either push or pull this sled so that he can do so with a minimum of effort? If you remember, the derivative is useful in finding out what's going on at a minimum or a maximum of function. So we're going to apply the derivative tool to this problem today. Let's get started. Let's go ahead and componentize the force of the kid in each case. Okay, if we look on the left-hand side, this is when he's pushing. Right, we can take this two-dimensional force and break it into its one-dimensional component, right, like that, and then in the vertical direction, coming down like this. Okay, and we can see here that right here, right, this is what's going to add to the normal force, right, because the ground's going to have to push up harder to compensate for that. All right, so what we're going to explore is at what angle should the kid push? Okay, at what angle should the kid push in order to be able to move the child on the sled forward with the least amount of effort? Okay, in other words, we want F to be as small as possible. Okay, and then if you come to the right side, we're going to do the same thing for the pulling situation. So if we componentize this force, it's going to look like this, right? In this case, because the kid is pulling up, right, that vertical component is actually allowing the ground not to push up as much, right? So since the normal force is less, the friction force is going to be less. All right, let's look at the example on the left first. Okay, I'll go to the next screen, and maybe we should quick draw those components again. Okay, so there's the vertical component, and there's the horizontal component, and let's make the actual F, let's make that the color red. So just to kind of keep with the color coding. So what I want to find is at what angle can that F be the smallest possible value. All right, so what we're going to do is we're going to write F equals ma for this equation, okay, in the x and y direction. Okay, F equals ma in the x and y direction. I'm going to pause right now and then write those out for you. All right, let's take a look. You can see on the on the right side, on the y side, I've basically derived the equation from the previous page, okay, which is that the normal force from the ground has to support both the weight of the sled and the kid, as well as that additional downward push, right? So the normal force is going to be greater than the weight in this case. And then what I need to do, right, is I need to take this normal force, okay, this term here, and I'm going to need to plug that in right there. So that's going to be a kind of a longish equation. Let me pause again and write that. Okay, let's take a look at what I've done. I substituted in the normal force on the y side into the x side, and then I factored out the F, okay, from these two terms here. Okay, I factored out the F there. And I'm going to go to the next page and continue working this equation a little bit. All right, on the next page, you see the same expression again. Now remember what we're after here. We're trying to figure out what's the smallest this can be to barely get this sled to start to move. So that condition, the way we can solve for that is we can basically set the acceleration equal to 0, right? 0.00001, effectively 0. So I'm going to set that equal to 0 and solve this for F. Okay, and I get the following when I move these things to the other side. I get this expression here. Okay, and what you have in effect is you have, let me rewrite F on the left side of the equation. What you have in effect is you have F as a function of theta, right? If you look at the expression on the right side, it's just constants, right? Mu, m, and g, and then theta. So you have F as a function of theta. Now, I think that you can figure out, without having to do all this math, what the ideal angle is to push at if you're going to push downward. Okay, I think you can figure out what the ideal angle is. It's a pretty straightforward answer. What I would like you to do on your own before you come to class next time is I would like you to make a graph, okay, of this function. Okay, so pick 5, 6 points and do a data table in which you plot f, right, for different values of theta. So, right, use some different values of theta and then have f here. And then I'd like to see a graph, right? When you come to class, I'd like to see a graph which looks something like this, okay? And from your graph, we should be able to see what the answer is, like for what value of theta f is the smallest, okay? That's basically how you work through it. The more interesting case is actually the other example when the kid is pulling. So let's take a look at that now, all right? So again, we're going to componentize, okay? And I want to make this force the red one, right? The component force, the composite force, the 2D force. And then we're going to componentize and kind of keep with our same color coding. Green's going to be horizontal. It's pretty short looking, doesn't show up very well. And our vertical, okay? And again, I'm going to pause and I'm going to write out the F equals ma equations. Okay, I think they're going to look obviously very similar to the previous example with a few changes in sign, right? Positives and negatives. Let me pause and do that. You can see that the left side, right, the x direction, okay, looks exactly the same. Okay, that's unchanged. But the right side, the y side, has a slight difference. Okay, now the kid is helping pull up, right? So now the ground doesn't have to push up as much. So you can see here that the normal force is less than the weight, right? This sign changed from a positive to a negative. I'm going to do the same thing now. I'm going to take this expression, okay, and I'm going to plug it in right there. And then I'm going to work out the same. I'm going to solve it for f again. All right, so let me pause and do that. I've done pretty much the same thing here that I did previously, is that I substituted a normal force. I factored out the f, okay, and again I'm going to move to the next page. I'm going to solve for f, and again I'm also going to set acceleration equal to 0 because I'm trying to find that minimum force, right, when it just begins to accelerate. Okay, you can see that the expression is identical except for in the denominator the sign is positive rather than negative. So what we want to do is we want to look at this situation as well. This case is a little more interesting. I don't think that the answer is quite as obvious. So we're actually going to do the hardcore math here and solve for what is the best angle at which to pull this object to get the sled to accelerate with the minimum force. Okay, listen to the word minimum, right? The word minimum should start to trigger in your mind a particular calculus word. That's right, the derivative. So what we're going to do is we're going to take the derivative of this function, right? Because we have a function of force with respect to theta, and we want to know for which values of theta force will be a minimum. So we're going to set the derivative equal to 0, right? Take the derivative and set it equal to 0. So now we're going to go into math mode, and we're going to take the derivative of this function, where you can see that the variable is actually all in the denominator, right? In this case, the numerator is just constants. So let's tackle how we're going to do that. We're actually going to go do a u substitution here, okay, where u is going to be our denominator in this function, okay? And then we're going to take the derivative of u with respect to theta, like so. And the derivative of cosine is negative sine, and the derivative of sine is cosine, like that. Okay, and then we can see that du is equal to this right here, like that, times d theta. Okay, so now it's time to come over to our function and make that substitution. Okay. So we have this here, and that's just going to put u on the bottom, okay? So what we want to do is we want to take the derivative of f with respect to u, like that, right? So you can see we're run out of space again, so I'm going to go to the next screen. All right, let's look at the next screen, Okay, I just wrote a few more steps out. Okay, I looked at 1 over u is just u to the negative 1, right? And so once we write it that way, that's a pretty easy derivative, right? We just subtract 1 and multiply that out. That's going to look like this. Negative mu mg times negative 1, right, times 2 u to the negative 2, like that. Okay? And so what I'm going to do is, obviously these cancel, right? Those negatives cancel. And now I want to go back and I want to substitute the u in. Okay, so let me pause again and write that out. All right, you see the next line here. And what I want to do now is I'm going to substitute back in for u, and I'm also going to substitute for du over here. Okay, and I'm going to do that right there. Okay, so this is really going to be d theta, and then our u from the front page. Let's look here. Negative sine plus mu cosine, right? Negative sine theta plus mu cosine theta, like so. And all of that equals this here, mu mg, and then we have that same expression squared, right? It's pretty boring stuff, okay? Just taking the derivative, though, all right? And again, remember what we're after here. We're after setting this equal to 0, okay? So here's the derivative we're after, which is df d theta, okay? And then I'm just going to take this denominator and move it up to the top, okay, like so. And after I do that, I'm not even going to write out the denominator, okay? Because I think you're going to see when we set this equal to 0, right? For the derivative to be equal to 0, only the numerator has to be equal to 0. So the denominator doesn't even come into play. So all we're really after, okay, and in fact, this is going to cancel out as well, right? So all you really have in terms of evaluating the derivative at the derivative equals 0 is setting that numerator equal to 0, okay? So we've got one more page and then we can get to our answer. So all of our math boils down basically to this right here. We want to find out for what values of theta, okay, is this equal to 0? And we get a pretty darn simple expression after all of this, right? Remember, if we divide both sides by cosine here, notice what you get on the left side. You get the tangent, right? Tan theta, and these cancel, equals mu. Okay, so to solve for theta, we finally get the angle at which the force is a minimum, right? For where the derivative is equal to 0 is this expression right here, mu. And we're talking about the static friction. I probably should have been carrying that the whole time, right? But this is the situation where the sled is just about to move, so we're working against static friction. So this mu the whole time has been the static friction mu. There you have it. Pretty darn cool. Okay, took us a little bit of tedious derivative algebra and calculus work, but there we have a pretty simple expression for the angle at which the force can be a minimum. Okay. I would like you to do, as a final step here on your own, I would like you to graph this function as well. Okay, so just like I asked you to graph the previous function, I'd like you to create a data table, plug in some different values. You know, pick some value of mu, right? Like a common value, say 0.3 or 0.4, and then plot different values of force, right, for different values of the angle. You're going to see this graph look a bit different than the other situation where the kid was pushing. Okay, when the kid is pulling in this situation, the graph's going to look different, and you're going to see that the minimum is at a different location angle-wise. There you have it, calculus and Newton's laws and perfect synergy.